Hello everyone, my name is Jarkko Lagus. I'm from University of Helsinki, and today I'm representing our paper, Learning to Lemmatize in the Word Representation Space. So the lemmatization is the task of text normalization, where we normalize each word of the document into the same basic form. This is often done as a pre-processing steps to get better results and gain some performance gains on subsequent tasks. And it's often done in this character level way, so that you edit the words themselves using some kind of a morphological analyzer that tells you what would be the basic forms of this word. It's often not vital for English language, where the inflectional complexity is not that high, but for morphologically rich languages it's often crucial for getting good performance on text tasks. And some of these languages are like Finnish, Russian, Turkish and Arabic. So as mentioned in the previous slide, it's usually done on the character level, so you transform the words in the sort of the character space, but we want to consider this to be done in the word embedding space. So because of in any way you would turn these lemmatized words in the word embedding space afterwards for subsequent steps, then why not do it already? Why not do it also in the lemmatization in the word embedding space? What we did is we took this approach and we learned supervised lemmatizer in this word embedding space, and we trained for each word class. We trained a separate lemmatizer. So here on the right you can see sort of the idea depicted in a simple pictorial format. So we just assume that there are these word classes, subspaces, that we can then transform into this lemma subspace. So essentially we reorder the traditional pipeline, moving the lemmatizer from as a pre-processing step as a part of the full pipeline. This streamlines sort of the processing in a way that you can just have one end-to-end model where this is kind of integrated to the beginning of the pipeline just after the word embedding encoding phase. And because we train individual lemmatizers, in order to lemmatize each word, we need to use chaining, and for this we introduce this novel idempotency regularization method that guarantees that we don't change words that are already in the right format into a different format. So the training process goes so that when we're given these word and lemma pairs, we aim to learn some kind of mapping, in this case a neural network, that there is these inflected word embeddings and turn them as closely to the lemma that we have paired it with. So this is done in a supervised way, so we need some kind of corpus easily accessible, at least for Finnish, from Wiktionary. So in order to approximate this, we define these 4 different variants, going from complexity to from simpler to more complex. So we went through with this kind of like very standard, lightweight model families, so linear without no activation functions, then a very simple one that has only 2 layers and 1 activation function. Then we have this compression layer, which is identical to simple one, but which will have less parameters than the word embedding dimensionality is. And then we have the complex, where we have 3 layers and 2 activation functions, and in this case we used the ReLU activation function in all of these. So here the R stands for the ReLU activation function. So what kind of requirements do we then set for this neural network or word embedding space-based lemmatizer? We wanted to satisfy two different criteria at the same time. So we want to be able to transform any embedding into its corresponding lemma. But we also need to make sure that if we have already lemmatized something, we don't change the embedding. So we get this two-part criteria, which both can be encoded into this two-part loss function shown here. So the first part of this is, of course, you have to have some kind of distance. So what we did, we just used a simple distance metric here, choosing the Euclidean distance because it preserves the scale of the embedding, so it retains in some sense more information. So the first part is just we use the model defined previously just to transform the embedding into as close as we can to the pair of it, the embedding lemma pair of it, and minimize the distance between them. Then the latter part of the loss function we define is the idempotency regularization. So as we want to have already lemmatized words as close as possible to the original meanings, we run the same transformation twice, which gives us a sort of second loop, which we want to be as minimally changing the loop again. And we call this idempotency regularization because it kind of it encourages to idempotency transformation. And we can just define it with using the same distance metric and the same model as before. So here it's important to use the same model as we would want to use the parameter sharing. So here we see the two-part function combined as a convex combination with the alpha parameter. And on the red you have the distance to the lemmas, and on the red you have the regularization part. And the range here, because it's a convex combination, the range of alpha parameter is from 0 to 1. So using these definitions, we ran 3 sets of experiments to see how the lemmatization works. So the first experiment, we just want to see is there differences between if we choose different architectures and what kind of regularization parameters are needed. Then in the second experiment, we went more towards like these real-world tasks, so measuring the document similarity using these lemmatized or using this lemmatizer as a part of our pipeline. And then we experiment on actually reversing the order of the training and training actually mapping from the lemmas to the inflected forms. And for all these we trained, for all the experiments we used the same models trained on Finnish fast text embeddings, and we defined the models using PyTorch, and the lemma pairs were extracted from the Wiktionary. So the first experiment, so for the architectural choices, we found out that almost all of the neural models work equally well, except slight performance drop with the compression network, which kind of shows that there is no, at least easy to find, subspace that would contain these lemma words. So it kind of suggests that you have to keep you cannot really touch the embedding dimensionality once it has been learned. And it seems like the idempotency in this case doesn't really affect to the lemmatization accuracy, so it just sets itself to the sort of the standard value. So the simple was the best model out of this, so this is what we then use in the subsequent experiments. So for the second experiment, we tried out this document similarity comparison. We had to create this kind of artificial dataset where we took a document, split it half and half, and then try to retrieve, combine all these end parts, and then try to retrieve for each beginning part the corresponding end part. And this is done by ranking, so for each document you compare all the n number of ending parts and then see which one is the closest. And what we saw that there is clearly the improvement in these document similarity measurements when our lemmatizer is imposed on the pipeline. We saw that chaining of these individual lemmatizers also improve the results. So you can just chain if you want to do lemmatize multiple word cases, word classes or word cases. Then you can just combine these using the regularization. It works, improving the results. We also realized that the regularization, while it's needed, it's not very sensitive to the parameter. So anything basically from 0.3 to 0.8 is valid range for the. So going 0.5 always seems to be like a reasonable choice. So what we saw, so individual surpasses traditional lemmatization, and the chaining will affect the results even better. And for the third experiment, we did this morphological generation. So we reversed just the order and saw if it can create appropriate inflected forms, and it does incredibly well in this case. So it is able to create all these in forms that were previously it's able to create all these forms that we tested it, and it returns the correct. When this sends measured to the correct lemma, it's the closest one. And this task can be useful, for example, if you have some kind of query expansion required for some task. For example, if your search engine doesn't support like word embeddings or doesn't do kind of smart search, so that it would know to look for these partial results as well. So to conclude, so it seems that the word embedding level lemmatization works extremely well, even surpassing the traditional lemmatizer, at least when measured in document comparison task and in Finnish language. Why we think this works is that it removes some of the noise, unwanted noise that is always there in the embeddings. So, and this is consistent within each word. And it seems that the lemmatization gives like a suitable proxy for removing some of this unwanted noise. The neural network method makes it very simple to learn these models, and they become quite lightweight. So this can be easily plugged into any kind of pipeline, especially if there are already neural pipelines. You can just add these as a locked pre-trained set of layers to the beginning, just after the embedding layer. And we can also reverse the method if we want to create this. If we want to generate inflected forms out of lemmas. And also our code is available if you want to take a look at. So we have there all the model definitions and all the required code to run these experiments as well. That was my presentation. I thank you all.